everybody. I think 9 o'clock is a bit early. I think it's a good time to start. So I'll be talking on this Mauna Kea spectroscopic explorer, basically on the galactic science. And most of my things are just culled from the science cases from the document of MSE that has appeared in 2019 in archive. So I urge you to look at that document, and it's a very nicely written all the science cases which the Mauna Kea spectroscopic explorer can achieve and meet. So some of the I feel it is like a advertisement talk for MSc, but I went through the document thinking I would learn something from that, and my aim would be the same for Euclid. So the salient features of this Mauna Kea spectroscopic explorer, which I will tell as MSc, is an end-to-end science platform for the design, execution, and scientific exploration of spectroscopic surveys. It will unveil the composition and dynamics of the faint universe and impact nearly every field of astrophysics across all spatial scales, from individual stars to large scales. We can explore the outer regions of our galaxy very effectively with this survey. Major pillars in the galactic science program for MSc include the ultimate Gaia follow-up facility for understanding the chemistry and dynamics of the distant Milky Way, including outer disk and faint stellar halo at high spectral resolution. So this will complement our Gaia data sets, and combining with data and the high resolution spectroscopy, we can do the chemodynamics of our galaxy with great precision. And then we could also study, which I will not, this is beyond my scope because I'm only talking about galactic science. So galaxy formation and evolution, which I think it must contribute to this field. The MSc is positioned to become a critical hub in the engineering international network of frontline astronomical facilities with scientific capabilities that naturally complement and extend to the scientific power of Gaia, the large synoptic telescope, the square kilometer array, Euclid, W1st, and 30-meter telescopes, and many more. So this MSc is going to complement the present day astronomical facilities as well as the ones which we expect in the future. So the instrument and its capabilities, the MSc Observatory has an 11.25 meter aperture with a 1.5 square degree field, remarkable 1.5 square degree field of view that will be fully dedicated to multi-object spectroscopy. MSc is designed for transformative high precision studies of faint astrophysical phenomena. So if you go, it will have multi-fiber things which will cover this 1.5 square degree field, and in one go it can take spectra of around 3,250 spectra. It will have these many fibers, and this will operate at two resolution mode. One is 3,000 and other is 6,000. These are medium and moderate resolutions, but it has a high resolution mode which will operate at 20,000 and 40,000, and this will be mainly for the optical region, which will cover from say around 3,600 angstroms to 9,000 angstroms. But then our fibers will reduce from 3,300 to say about 1,100, but remarkable if you look at the number of fibers for the high resolution things and for the low resolution. And for the low resolution, it will do the survey for optical as well as J and H bands. And all spectrographs are available all the time. The entire optical window, which I mentioned, is from 3,600 to 9,500 angstroms. And the near infrared J and H bands will be accessible at lower resolutions, and windows of the optical range will be accessible at the highest resolution, which I mentioned, that is from 20,000 to 40,000. So one of the key sciences which MSE will address in stellar and galactic scales, MSE will be the most powerful facility available to provide critical stellar spectroscopic observations for stars across the HR diagram. MSE stellar monitoring programs will dramatically improve our understanding of stellar multiplicity, including providing dynamical masses of unprecedented sample of transiting hot Jupiters. Look at the number, it is 10,000. It will be, I think, from the present surveys, it will increase the order of magnitudes. And we would also explore many binary and multiplicity in our stellar sources. MSE will study the R process element abundance across our galaxy. A very important thing which needs to be addressed, still an open problem. What are the sites of R process? MSE will produce the definitive data set of most chemically primitive stars to explore and identify the signatures of the very first supernovae and chemical enrichment events in the universe. So it can go faint, it can catch metal poor stars, and then from its chemical composition, one could find out how elements are produced and what would be the yield of your first supernovae. MSE will carry out the ultimate spectroscopic follow-up of the Gaia mission, and it is the only facility capable of producing vast high-resolution spectroscopic datasets for stars across the full magnitude range of Gaia targets. So from bright 16th magnitude to you can go up to 20, 22. It depends on what kind of work you want to do. High resolution, you may be a bit limited, but for the low resolution, you can go much fainter. So MSE is critical to our understanding of the faint and distance regimes of galaxy, in particular the outer disk. So you can actually explore the various components of our Milky Way, like the outer disk, thick disk, and the stellar halo. And will conduct in situ chemodynamic analysis of millions of individual stars in all galactic components. Most of our studies had been in the solar neighborhood, but this will have the in situ chemodynamic analysis, which would be remarkable. It will play a central role in evolutionary three-dimensional ISM mapping experiments that will be boosted by Gaia parallax distances. In different line sites across the galaxy, you can actually map the ISM, provided you have bright hot stars in the background. MSE will also usher in a new era of studies of nearby dwarf galaxies. It will enable accurate and efficient chemodynamical measurements across their full luminosity range and will provide spectra for more than an order of magnitude more stars in each system. So it will actually outsmart the present surveys by at least an order of magnitude. The Monarchia Spectroscopic Explorer will address key science cases ranging from time domain searches of substellar mass objects and understanding the statistical properties like exoplanetary hosts. We had a talk yesterday of stars hosting planets to determine the properties of the dark matter in dark matter particle and measuring the mass of neutrons. This is, how it will affect the present day cosmology. Key science cases that MSE would address: the composition and dynamics of the faint universe, as I discussed earlier, exoplanets and stellar astrophysics, chemical nucleosynthesis, the Milky Way and resolved stellar populations. So as I was mentioning, the composition and dynamics of the field universe, you see how, see till now the exploration, if you say with the 4-meter class telescopes are limited to your optical visual magnitudes of around 16. In the MSE era, you could explore fainter than 16. This is where your disk would be. You can go into the outer disk, your thick disk, and in the outer regions of the halo. So look at this region. It will contribute enormously in these fainter regimes. And so as an 11.25 facility, MSE will obtain good signal to noise at high resolution in reasonable exposure times across the full magnitude range of Gaia targets, including where the stellar halo is dominant. So that is at visual magnitude of about 9.5 at high galactic latitudes. Exoplanets and stellar astrophysics. So located at the equatorial source, so this is at the galactic latitude of our latitude of around 20 degrees, where this MSE will be present. So MSE will access the entire northern hemisphere and half of the southern sky, making it an ideal follow-up and feeder facility for a large number of both existing and planned ground and space-based facilities. MSE will be the most powerful facility available to provide critical stellar spectroscopic observation from the lowest mass brown dwarfs to massive OB star type giants, and including important yet the stellar types across the HR diagram, such as solar twin studies, CFITs, RR Lyrae, AGBs and post-AGB stars, as well as metal poor white dwarfs. So it can study almost all objects across the HR diagram. I mean the faintest limits where we are not much aware of what physics is going on. In the stellar regime, strong synergies exist between MSE, TESS, Plato, Gaia, Rosetta, LSST, and other time domain facilities. MSE stellar monitoring programs will dramatically improve our understanding of stellar multiplicity, binarity, and multiple objects, including the interaction and common evolution between companions spanning a vast range of parameter space, such as low mass stars, brown dwarfs, exoplanets, pulsating stars, eclipses, and eruptive variables. MSE will provide dynamical masses for unprecedented sample of transiting hot Jupiters, which I mentioned will be around 10,000 in number. MSE will be crucial to constrain the poorly known aspect of stellar physics in the low mass domain in this regime, less than half solar masses, including the equation of state, dense gas, opacities, nuclear reaction rates, and magnetic fields. So look at this plot. So where your MSE stands, these are upcoming facilities. These are all what you have. So if we have MSE, it will be really remarkable. So MSE will dramatically improve the resolving power and sensitivity of past, current, and future planned surveys to characterize stars, substellar objects, and exoplanets. So this is a plot where it is a function of resolving power, wavelength coverage, central wavelength, number of fibers of high resolution mode, and field of view, and with respect to the resolving power. And so exoplanet host stars can be studied very well. Stellar physics with star clusters, open clusters, globular clusters, white dwarfs will be the another regime which MSE will explore. See, look at the distances it can go. So if you have cool main sequence stars, it can explore to 1 kpc. If you have the hotter main sequence stars, MSE could explore to 10 kpc, and at the turn off, main sequence turn off, it can go almost up to 100 kpc. A similar diagram for this is for open clusters. This is for globular clusters. Similar thing is shown how deep one could trace, how the different stellar populations could trace.
This is the what resolution.
This is it all depends on it. I think that the this is made for the low resolution as well as the high resolution things. But if you want to go to the deepest to larger distances, then it will have limitations in resolution.
If this figure stands for which resolution?
The figure stands for the maybe to be correct, it would be for the medium resolution because it spans from faint to bright. So to these distances.
Understand because it's put in the absolute magnitude scale.
Yes.
So I don't know actual magnitudes involved there. This is an absolute magnitude scale. I don't have the sense. That's why I'm asking. You can take it.
So how I understand is, see for the main sequence stars in the globular clusters, it could trace up to 5 kpc with MSE with say a low resolution spectrum. And say if you go to 25 kpc, your turn of stars can trace up to distance of 25 kpc. And if you have giant stars, then you can go a maximum.
That's not my point. Is that depending upon distance?
Yeah.
Some clusters are nearby, some clusters are far away. So
Yes.
They're not the same magnitude.
So that
this is built into the system. I couldn't understand.
So
this is later.
Yeah. So this is actually this is actually what would be the absolute magnitudes of the main sequence stars? What would be the absolute magnitudes of the giants? What would be the absolute magnitudes of your RGB tip? So this is generated by taking the absolute magnitudes. So this is the overplot of all the globular clusters which are at different distances. So this is an integrated plot.
Yeah, I understand. So that's where I lost the sense of distance and lost the sense of magnitude.
Yeah, you would actually would be better to answer this.
No, I lost the sense of magnitude. So,
So this is the absolute magnitudes for the main sequence,
yes,
for the giant and
what resolution, since it's not
so
what I'm asking.
yeah. This resolution, as I told, for me, I think doing high resolution at 30,000 would be difficult, maybe for the brightest ones, and also it depends. So that's why I made a statement that for the low resolution, this will hold. And then stellar astrophysics, the astroseismology studies rotation and stellar activity, which MSE will contribute. Multiple star systems like the binary senses of the Milky Way. Our main understanding is we treat stars as single stars, but they will be multiple objects, binaries. Now things are evolving, and 40% of our universe is basically binary. So this will tell us much more on the binary nature of our universe. Compact white dwarf binaries, asymptotic J branch evolution. This will contribute. Not many AGBs are known compared to normal stars, a main sequence, RGBs. So AGB stars go through rich nucleosynthesis during various cell burnings like hydrogen, helium, and the various nucleosynthesis processes happening at those shell burning phases, and the complex mixing to thereby contribute to the chemical enrichment of the galaxy. So MSE will contribute enormously in the asymptotic J branch evolution. And then very metal poor stars. Yesterday you heard the talk from Shivrani. So you know where metal poor stars stand in contributing to the chemical evolution of the galaxy and understanding the various formation of elements. So coming to chemical nucleosynthesis, so metal poor stars and the first chemical enrichment events in the universe. This is what you will study from metal poor stars. The cosmological lithium problem was described by Shivrani yesterday, so I will not delve into it. The promise and potential of chemical tagging to probe the origin of elements, sites of I process and the origin of temp R and S stars. So usually we think either it's R process, neutron capture, or slow process neutron captures, but in some of the metal core stars, which are called CHEMs, they have a mix of R and S, and which can be explored by something called I process based on their neutron flux, which is in between R process and S process neutron fluxing. So in this area, MSE would contribute enormously. Studying AGBs and their progeny, survey of R process elements, very important, because still in Sun we have the R process is still unknown. What are the sites? We have some ideas, but we have to still work on it, and I hope MSE will throw more light on the R process elements. And the Milky Way and the resolved stellar populations, the same what I was telling, the chemodynamic evolution of the Milky Way. So how would you trace them from the ton of stars which are shown in blue, and what magnitudes they would sample, and from the horizontal branch giants is this region they can trace, and from their spectra we can tell from how what abundances they give, and they give us the information of that particular region, and that the whole galaxy can be mapped. And with metallicity you can study how our Milky Way is evolving. So MSE will play a crucial role for understanding the otherwise least accessible part of our galaxy, the faint and distant regimes where the outer disk, thick disk, and stellar halo are dominant. And quickly, what else the MSE will do? So this, which I had been telling, in situ chemical tagging of the outer galaxy, first stars and progenitors of the Milky Way, and then the main other important thing what MSE would contribute to is the interstellar medium and the 3D mapping of the galactic ISM. So these are some of the tracers, some of the tracer like these sodium one doublet, the resonance lines, which would be very strong. So if you have hot stars in the background, the ISM can be nicely traced by these diagnostics. These are molecules, these are some of the DIBs. So the ISM will be studied as part of the observations that will be planned for the Galactic Archaeology Survey, with more than 1 million sight lines spread across the sky. The ISM survey would be extremely efficient, since high quality spectra of signal to noise 100 could be obtained in just 15 minutes exposure for G16 stars of spectral type OBA. So this Annapurni, this may give you an idea. So this kind of say so this is for a high resolution of say 20,000. So one could get a signal to noise ratio of 100 in just about 15 minutes for a visual magnitude of 60.
This is for high resolution.
This is for high resolution.
Like what are?
Pardon?
What are it?
R would be 20,000. It has though 20,000 to 40,000. So this is just to be in the safe side, I say low resolution. So 20,000.
40,000 is optical and 20,000 is infrared.
No. 20,000 is the red region of the optical, and blue region is 40,000, and in the infrared J and H bands it is around maximum is 3,000. Minimum is 3,000 to 6,000. But 3,000 and 6,000 you have in optical also, including the high resolution thing. I think I am done. I think it is so nicely written. That document I think runs several pages. So in fact, I could not find time to put in what my interests are. It is so well written that what I do is totally sidelined. It's remarkable, a very good read. Maybe you should go to that document, 2019 MSE Science document. It's a very good read. I recommend that. Thank you.
We have a couple of questions.
This all. This is on the instrumentation side, but so you said you can visit the hot Jupiters with MSC, right? So I thought 40,000 resolution has not a full wavelength cover. It's in different spectrographs, small pieces of wavelength. So what kind of calibration that you need, you know?
You should be answering that. What I as I told you, I didn't particularly look at how they will do, but in the 40,000 resolution mode, what I don't even I didn't go into the depth of the paper. I don't know what are the calibrations. I think they may have some cones.
That may be because it's small.
I'm just guessing.
But that may be a
Yes.
So, sir,
Thanks for the nice talk. Yeah,
Yes.
I have a couple of quick questions. First one is, what is the procedure to detect terrestrial exoplanets by this image imaging? The second one is, can we study particular atmosphere in great detail with this?
Yes, that's what I read from the document. See, this is not my subject of interest. This is basically an advertisement of MSc, and I am just presenting what is written in the document. To depth, actually, I would like to learn from you because you work on exoplanets. Yes, it will explore very nicely the atmospheres of Jupiter. And because you can actually observe the resonance lines during the transit, and it will tell how your atmospheres, molecular lines, infrared lines, many lines you can use.
How much resolution we can get?
The present resolution is 40,000, the maximum resolution. Okay, because it's a survey telescope, but the maximum, if you have a target to observe and study, then they can have with 40,000 maximum.
yeah, maybe we can have one more question.
Hello, sir. My question is regarding, you said around 1,000 to 3,000 objects we can have the spectrum.
In the low resolution
More
mode,
than 3,000.
you can have 3,100 in one go.
Yes, and the field of view is something like
1.5 square degree field.
square degree. Now my question is, what type of detector they are using that, suppose in a 1.5 square degree, how many stars can we get within a certain magnitude range? Like,
They will have several spectrographs connected to these fibers. Maybe in the low resolution, they may have order in one detector, but for the high resolution, they will have several spectrographs for each star.
Yes, like my question is, actually, will there be a magnitude range for a particular exposure time, something like that? Because suppose there is a 9 magnitude star, there is 18 magnitude star. Both of them are far away.
Yes. So what I see from the Gaia, they know roughly the magnitudes. Okay, so they will observe the field keeping in mind the magnitudes of the star. I guess so. I think that's how.
There are more questions we can discuss with.
Long live India and France friendship.